Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to the course on computer aided drug design. We will continue on the concept of drug properties, and we will also look at something called SMILES, S-M-I-E-L-S. So, in the previous class I had talked about properties, important properties, the drug absorption, okay, volume of distribution, it is called absorption not adsorption. Oral absorption, because most of the drugs are taken orally, and then volume of distribution, it gets distributed into the blood stream as well as into the tissues. The metabolism, how it gets metabolized, how it gets excreted, is it have solubility at pH is equal to 2, that is your stomach, and does it have solubility at pH is equal to 7, that is in the blood region. Bioavailability, what is the concentration of the blood available at the target site, does it have side effects, toxicity, stability at pH 2 and at 7, the blood brain barrier penetration, BBB means blood brain barrier, and then PGB efflux. So, many of these properties are given in many of the databases. I will show you as examples also now, as well as there are some softwares, online softwares, where we can calculate theoretically some of these properties. So, we will look at some of these databases like Zinc 15, Drug Bank, Drugscom, PubChem. So, some of the data are of these drug properties are available, and this particular Swiss ADME is a software where we can calculate theoretically some of these properties, not all of them, some of these properties when we draw a structure. Okay, let us look at some of these examples as of now. The first one is your zinc, zinc 15, as I said, zinc 15, I just typed in aspirin. Okay, aspirin is a very common drug, it is for antipyretic, pain, it is also used for platelet deaggregation and so on. So, this is also known as the acetyl salicylic acid. Now, as you can see, some properties are given: net charge, hydrogen bond donors, that means does it have any donors like OH, NH, but this OH is not considered as a donor because generally it dissociates into O minus and H plus. Hydrogen bond acceptors, it has got 1, 2, 3, 4. Total polar surface area, is contributed by the oxygens and nitrogens. Rotatable bonds, it has got 2 rotatable bonds, okay, basically these and all that. Desolvation, the polar desolvation, the apolar desolvation and polar desolvation. So, some properties either experimentally determined or properties which are obtained from theoretical modeling are given. In addition, I think other information is also given about this molecule. Now, let us look at another database. This is called the Drug Bank database. As I mentioned, this is Drug Bank. This molecule is called acetaminophen. It is like a paracetamol, it is a paracetamol. So, it can be used for analgesic, antipyretic. So, okay, these are the applications it is used. It does not have anti-inflammatory, anti-platelet activity, but it can be used for antipyretic. So, if you look at some of these properties of this particular database, also gives you some properties, the molecular formula, okay, and as you can see, some of the route of elimination, half-life, clearance, some toxicity, metabolism, what type of enzymes metabolize, what is the absorption of this, rapid and almost complete. So, immediately it gets absorbed, okay, then which organisms get, then is there any interactions, okay. So, a lot of information, as you can see, are given about the log p values. Let me talk more about these log p. Log p is nothing but the hydrophilic balance of the drug, and log P is it tells you how much hydrophobic the molecule is so that it can cross the lipid bilayer in the gastrointestinal tract, and the hydrophilic determines the solubility of this. So, higher the log P more hydrophobic it is, lower the log P more hydrophilic it is. So, this is a very hydrophilic molecule. So, these log P's are calculated by two different softwares. Then log S is the logarithm of the solubility, pKa dissociation, as you can see pK is strongest basic, so many things, hydrogen bond acceptor count, hydrogen bond donor count, polar surface area, refractivity, number of rings it has got, bioavailability. So, it is very good bioavailable, and then you can see blood brain barrier, yes it may cross blood brain barrier, very high probability. Human intestinal absorption, again it has got very high probability. P glycoprotein substrate, no, so it does not. And then biodegradation, readily biodegradable, toxicity details are given. So, if it is a drug, then we can use the drug bank, and also other one I talked about drugs.com. So, we can use that also, and you will get experimental data as well as theoretically estimated data using different types of correlations. Now, another software which I said is the NCBI database, which I mentioned, ncbi.nm, nim.nih. So, we can use that. For example, I typed metformin here, so it gives you a molecular formula, okay. It is biguanide, so it gives a lot of chemical details about it. Okay, then it gives you toxicity, we can click on this, so it can give you toxicity, safety, hazards, okay. Then it gives you a 3D conformation. Okay. As you can see, again molecular weight, hydrogen bond donor count, it has got 3 hydrogen bond donors, okay. So, it has got this one, okay, this one and this one, 3 hydrogen bond donors. Then it's got hydrogen bond acceptors, okay, how many heavy atoms it's got, hydrogen bond acceptor count 1, okay, because only one acceptor, okay. So, hydrogen bond acceptors, then rotatable bonds, 2 bonds, topological polar surface area, mass, log P, heavy atom count, and so on. Actually, as you can see, lot of properties. Then some experimental properties, melting point, okay, what it is, solid or liquid, vapor pressure data, log P as I said, more negative it is or more lesser the value, it means it is highly hydrophilic. As you can see, it has got a lot of nitrogens, right, and stability, stable under recommended storage, decomposition details, pKa, okay. So, that is the dissociation part of it. So, lot of information is given. So, experimental and theoretical. So, we can get many of these properties of molecules which are stored either in zinc database, or if it is a drug we can go to drug bank or drugs.com or even PubChem database. PubChem can also look at new structures. For example, if I have totally unknown molecule and I want to know some of these properties, I can find out using this particular software. This is called a Swiss ADME software. So, I can draw a structure here, okay. By drawing the structure I can say or try to predict some property. For example, I can draw the structure. So, I put in a benzene ring, then I put in this one, then I put another one, then I put some oxygen here, okay, and then I put so I put a tertiary group here, then a OH here, okay. So, this is a structure I have drawn. Imagine, yeah, this is a structure I have drawn, you understand. Then I want to know some of the properties which it can calculate. So, it converts it into something called SMILES. We will talk about this more in detail. SMILES is a representation, a linear representation of the molecule. Okay, we will talk more in detail after a few minutes. So it converts that into SMILES, then we can say run. So run, so it does a lot of calculations. Okay, as you can see, formula, molecular weight, this is the molecule which we have drawn, number of heavy atoms, okay, number of heavy atoms, that is carbon, nitrogen, oxygen, like that. So you have 6 carbons here, 7, 8, 9 and 1 oxygen, that is why 10. Okay, then rotatable bonds, okay, this bond is rotatable, that is why 1. Number of hydrogen bond acceptors, that is this oxygen, hydrogen bond donor, the OH, then total polar surface area is given here. Log P, there are different softwares which can give you log P. So as you can see, each software gives you some different values, and average log P, then solubility, log solubility, okay, and as you can see, when you say solubility class, if it is less than 4, as you can see here, it is soluble, and then different types of solubility. Then GI absorption is very good, high. BBB penetration, again it penetrates through the blood brain barrier because it is a small molecule. PGB substrate, it says it is not a substrate, and then does it go and bind to the cytochromes, okay, yes, no, no, no. Then we will talk about this, some of the drug likeness property they are called. There are different rules like Lipinski's rule, Gauss's rule, Weber rule, and Muge rule. We will talk about all these rules, and then later on, and then bioavailability. So 0.55 is good actually. So it is bioavailable. Lead likeness, does it have a lead likeness property? Yes, it has got a lead likeness. Synthetic, this is for a chemist, is it easy to make it or very difficult to make it? Okay, so it gives a lot of information for new molecules, it is very useful. So I feel it is got too much hydrophilic. If I want to reduce the hydrophilicity, I can draw another, modify the structure, and so on actually. So I can do many things and check it out and see whether I can synthesize this molecule and take it to my lab and start synthesizing. So this Swiss ADME is a good free online tool. So we can draw any structure here, we can even import structures from different softwares, as you can see, import. So we can import from different softwares, also different okay, softwares with the files with the different extensions we can import, okay, and then we can do a lot of calculations as I showed you below. So this molecule which I have drawn appears to be good. It has got good lead likeness, it has got good bioavailability, but it can penetrate the blood brain barrier, okay. So that is one of the problems of this particular molecule. So I can say modify a little bit, for example, then I put something like this, and then I put this, then I put this, then I put this, then maybe I put this, okay. Okay, so I have instead of OH I made it into a OCH3, so it's it will become more hydrophobic. Let us see what happens to it. Okay. So I run this molecule. So molecule 2. So this is the molecule I have drawn. So BBB still it is penetrating. As you can see, log P has gone up to 2.87. Bioavailability has not changed much. Okay, number of heavy atoms has gone up to 11 because we have added one CH3. Total polar surface area has come down about 9.23. Okay, solubility is still good, soluble, it's still soluble, it's BBB penetrating, GA absorption is still good. So, we can draw different types of structures, okay, and then see how some of these properties change, and then we can select molecules which appear to be satisfactory. So, we can start with the one structure and then slightly modify using this software, and then select a structure which seems to satisfy most of these rules. Some of these are, most of them are theoretical in nature, so there is going to be a lot of errors there, but still it gives you a first hand idea about what type of structures to select and which are the issues that particular molecule may face. Okay, now let us look at these smiles. What does this smiles mean? Okay, what does this smiles mean? Smiles, the expansion of that is simplified molecular input line entry system. SMILE, simplified molecular input line entry system. So, in single line we can describe the entire molecule. Atoms are represented by the standard abbreviation of the chemical element, okay, in square bracket, especially if it is gold, because it has got two okay, alphabets AU, whereas C is one alphabet. So, you do not need like this. Okay. So, it can be omitted for boron, carbon, nitrogen, oxygen, phosphorus, sulfur, all those things. Whereas other elements, if it has got two characters, we need to enclose with the square bracket. If the brackets are omitted, the proper number of implicit hydrogens are assumed. Okay. So, hydrogens are automatically assumed, you do not have to put. Smiles for water is O, because it assumes that O has two valency, so 2 H's are assumed. Bonds between aliphatic atoms are assumed to be single, okay, unless it is specified. For example, if I take cyclohexane, I will say C1, C, 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 C1. There are 6 carbons, okay, and then when I put this 1 and 1, that means this and this are bonded. So, it gives you a cyclohexane. Whereas, if I want to hexane, I will remove these 1 and 1. So, I will get 6 carbons. So, it is a hexane. Dioxane, so I have O1, then CC, O1, CC, and then again O, CC, okay, 1. So, this one and this one are connected, okay, this O comes in the middle, okay. So, it has got 4 carbons, that is why you have 1, 2, 3, 4 and 2 oxygens. And branches are described in parenthesis. So, I want a ketone, so I have 3 carbons and there is a double bond O on this carbon, as well as there is a single bond O with this carbon. So, as you can see, I have an acid here, okay, that is a propionic acid. So, I have carbon, 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 this carbon has a double bond O and this carbon also has a single bond O. For fluoroform, so we have carbon, there is a F with this carbon, there is another F with this carbon, and this carbon and F are connected. So, fluoroform. Okay. Aromatic are shown with lower case. So, aliphatics are shown with higher uppercase, aromatic. So, benzene I use just like cyclohexane, but only thing is instead of capital C's I use small c's, you understand. So, pyridines I start with nitrogen 1, then I put 5 carbons and then the last one I put 1. So, this carbon and this N are connected, and because they are all in lower case, it is an aromatic system. Furan, okay, it is a 5-membered oxygen, okay. So, I start with O1, I put 4 carbons and then I put 1. So, this carbon and this O are connected. Biphenyl, okay, so 2 benzene rings connected like this. So, I will close this benzene ring, then I will have another benzene ring and then I connect them, understand this one. And 3-cyanoanisole, this is the structure. So, I have a benzene ring, okay, and then there is a O CH3 connected and there is a carbon nitrile C triple bond N connected. Triple bond is put like this, double bond you can put, but triple bond it is put like this. So, you can see CO, that is it starting from there, from that corner, this corner, COC, that means you are coming here, and then this C1 is like this, and then you have C1 C triple bond N. Okay. So, this C1 means here, and then C triple bond N, they are all connected. Okay. If you have cyanide and OH here, CO here, this corresponds to this, and then CC1, okay, then CC1, then C triple bond N. So, if you have stereochemistry, configuration of double bonds is specified using this or this. So, if I put like this, it means trans difluoroethane, that means these F and F are in the trans form, that means okay, it is in the trans form. Okay. If I put like this, that means the F and F are in the cis form. Okay. Tetrahedral carbon is specified by like this or like this. Okay. So, if you have a L-alanine, so you have this bond coming out, so you have two of them. If the bond is going in, you have one of them. So, when you have two, it indicates that viewed from nitrogen along the bond to the chiral center. Okay. So, you can see this very clearly, D-alanine. So, we have the carbon at the hydrogen inside. Dinitrogen N triple bond N is shown like this, methyl isocyanate. Okay, methyl isocyanate, as you can see here, CH3N double bond CO. So, we show CN double bond C double bond O. It is very simple. Okay, what about inorganic? Copper sulfate Cu2 plus SO4. So, you put like this, Cu2 plus 2 with a square bracket, there is one bond, O with the minus, and then we have S. Then S is connected with the double bond O, and again double bond O, and then there is a square bracket for O minus. You understand? Vanillin. So, we have this O, okay, double bond C, that is this connection, and then you have the C1 C, and there is a O connected here, and then there is a C again O C, that is this connection, and then this closing here. Understand? Okay. So, this is shown here and this is shown here. So, look at this, you can spend your own time and do it. So, you open up somewhere and then you start from here. So, nitrogen 1, from one corner you are starting and drawing it. Okay. So, it is the beauty of this smile. Nicotine. So, we have the nitrogen here, this nitrogen, okay, nitrogen 1, and then we have lots of carbon, this carbon, these carbons and nitrogen here, and then there is a connection here. So, we have two rings here. So, this is related to the ring 1, this is an aliphatic system. So, the carbons are capital C, and then with that at H, okay, and then there is a closure here, and then this is the aromatic system, okay, they are connected here. Do you understand? This represents the aromatic system, this represents the aliphatic system, and so we have two rings here, and then C at H represents this. Resveratrol, it is found in grapes, blueberries, raspberries. It is supposed to have antioxidant activity, it has got very good prevention related to age related problems, heart disease, insulin. So, a lot of things are there. So, I want you guys to practice it, or we can even check it out here. Look at the smiles notation of this. We can look at the smiles notation of chalcones also. Okay. So, let us try that. We can just try this smiles notation here. So, we can use this particular software to do that. I want to show you guys how it is done. So, chalcone we can draw. So, we have a benzene here, we have a single bond, then then we have another single bond, then we have a double bond made out of this. So, we have this portion here, then we have this portion here, okay. So, little bit delays on that. So, we have this done. So, we need to add a benzene ring. Okay, so this is chalcone. So, I want to see this new structure, so you can see this, okay. So, this is the Smiles notation for chalcone here, okay, clearly it is given here. Okay. So, like that we can draw structures, we can create, and then the other advantage is we can copy Smiles notation from one software to another software. For example, I can go to zinc database, as you can see substances, and we can put in the Smiles notation. So, you can get the Smiles notation, okay, ignore this part, okay. Okay, so we can get the Smiles notation copied from one, and then we can get this, then we can try to get properties of various molecules, okay. Once we draw it in zinc database, we can use other database and find out if there are any properties existing. So, Smiles notations we can copy and get the structure of molecules, okay. So, that is very simple to do rather than actually drawing structure. So, we can move molecules from one database to another using this Smiles notation, okay. So, you can see this Smiles notation for this particular molecule, okay. So, we can move the Smiles notation from one molecule to another, as you can see here, okay. So, a lot of these type of details are given, okay. So, we can move the Smiles notation from one software to another and get properties if they are available, or we can search for similar structures if they are available, okay. Okay, so we have C4 hydroxy chalcone. So, those structures are there, chalcone, okay. So, we can look at this chalcone, we may get more properties from this particular database. So, this type of Smiles notation, so you can get some details about this particular molecule, okay. Properties, hydrogen bond acceptors, polar surface rotatable bonds. So, Smiles notation that way is very useful. It is just a string of characters which describes the structures, and we can move this Smiles notation from one database to another to get more if any information is available in another database. So, instead of drawing the structures, we can use this Smiles notation. So, Smiles notation is extremely useful. Once more, as I said, atoms are represented by stranded abbreviation. So, for bromine, carbon, nitrogen, oxygen, phosphorus, sulfur, fluorine, chlorine, boron, we do not need to have brackets, okay. Hydrogens are implicitly assumed. If it is an aromatic, we use a small lowercase. If it is an aliphatic, we use uppercase. So, if you have C1 and C1 coming in the beginning and end, that means there is a bond, this is a ring, okay. And then if you are enclosing with a parenthesis, that means this is a side chain. So, this is typically there is a ketone connected to the third carbon, that is what it means. And we can show stereochemistry, we can show the transforms by putting a slash in this form, we can show the cis form by putting slash in this form. We can also have okay, we can also show the enantiomers by putting either single symbol or double of this symbol, okay. So, Smiles notation can represent any type of molecule, and as I showed you here, if I use Swiss ADME and draw a structure, automatically it gives you the Smiles notation, and then we can use that Smiles notation and take it to different databases and try to get properties of that particular molecule. Okay. So, we will continue more on these drug properties in the next class as well. Thank you very much for your time.